All right, this is your third video on 5.3. This is example problem number 20. Okay, you have a 3 by 3 matrix. Okay, A is a 3 by 3 matrix. We need to find out what is eigenvalues, what are the eigenvalues and eigenvectors. So let's look at here. So this matrix, again, we're going to write down A minus lambda I like that. Okay, so that means A. So all the diagonal elements, you subtract lambda, isn't it? This is your lambda I. So when you subtract, you're going to see like that. This is your A minus lambda I. Now we find the determinant of that. So determinant of that equal to 0. So when I simplify that, you're going to see like that, right? So now I know it's third degree polynomial. You can use your algebra skill from your algebra class, or in the exam, you don't have to worry about this one. I'm going to give you this, how to solve this one. But anyway, there's a couple of different ways you can do that. And you can find the solution of this one, which is eigenvalues, which is 1, 2, and 3. Okay. After you find the eigenvalues, let's see when eigenvalue is 1. So your this matrix looks like that, right? So again, A minus lambda I matrix looks like that because you replace lambda by 1, and you're going to see like that. And dx x, y, z, there are 3 variables, and then you're going to put like this, right? So this is your you're trying to find the eigenvector. You're trying to find the vector for lambda when lambda is equal to 1. Okay, so first thing is I'm going to change this matrix to reduce row echelon form. I know you might have to do this one few steps, but that's a final answer. You can pause the video and you can do this one. You should be able to see something like that. Okay, now after you figure out your reduce row echelon form, so what you're going to do is now you're going to write down the equation. So if I look at this one, this is like a x times 1, 0 times y, and then half times z, right? So it looks like that, first one. And then second one, there's 2 equations. There's a free variable is what? There's a free variable is, again, is z. Z is your free variable. Okay, so just so that's why you write down like that. So x, y, z, you set it up, equal to z is a free variable. That's only one free variable. You're going to write down like that. And remember that z has to be 1, so just going to stay 1 here. And look at the equation. So if you look at this equation, so x equal to negative half z. So x has to be negative half times z. So z is 1, so that should be half here, right? Or did I do wrong? Not right. So if this is positive, this has to be negative, whereas this has to be negative, right? This has negative, and then y equal to half z. So that means this should be positive. Sorry, my bad. This is like that. So that's your z, and that is your eigenvector is 1. Or now, okay, either you can write down negative half, half, and 1, or you can write down negative 1, 1, and 2. You can write down this. So that's a negative 1 and positive 1, and that's a 2. So when lambda equal to 1, that's your eigenvalue and eigenvector. Okay. Similarly, if we do lambda equal to 2, you're going to see this eigenvector. When lambda equal to 3, this is a good practice for you to practice before, okay, before you start your homeworks. All right, and you can always check this one. This is your A times your V equal to 3 times your vector. So it's always going to work, right? Just make sure you check that one. So did I do, yes, 3? Yeah, I'm just checking for 3, right? So you check that one. So these are the eigenvalue and eigenvectors. Okay, let's do I'm going to talk about eigenspace here since we have a little bit of time here. So what is eigenspace? So eigenspace is the span of the eigenvalues, eigenvectors, right? So for each eigenvalue, from linear transformation from V to V, along with the 0 vector, the eigenspace is a vector in the V, right? So vector in the V. when TV equal to this one. So what is the, in a short way, is like you're going to span of the eigenvector. Eigenvector for the particular eigenvector for that particular eigenvalue. Okay, so let's look at here. And one other thing is like for distinct eigenvalues. So if the eigenvalues are distinct, they are not the same for n by n matrix. So that means these are the eigenvalues. So there are like a p number of eigenvalues. They are all distinct. Or there should be n number of eigenvalues. They are all distinct. And eigenvectors, whatever eigenvectors you get, this one, these are they form the linearly independent vectors. Right? They always form the linearly independent vector. And on another note, I already talked to you about this one. If the characteristic equation produces a multiple eigenvalue, so that means repeated eigenvalues, right? The dimension of the eigenspace does not necessarily correspond to its algebraic multiplicity. It doesn't mean like if there is like a repeated eigenvalue, doesn't mean that there's going to be that many number of eigenvectors. It doesn't mean that, right? So that is a double eigenvalue does not always have two-dimensional eigenspace. It doesn't mean that, okay? Just like this example, we have already done this one. So let me just look at this one. So remember that this is from the last example. So your A was 3, 2, 2, 0. This is your A. And then we got the eigenvalues are -1 and 4. And then eigenvectors were -1, 2. You can check it. And then 2, 1. I think 2, 1 is for 4. And then this is the eigenvector. So what are the, so if you look at here, these are the eigenvectors, right? So what they're saying here is eigenspace for lambda equal to -1 is span of -1, 2. Eigenspace for lambda equal to 4 is span of 2, 1. All right, so that's what the eigenspace is like. Now it's just a multiple of this one. It could be anywhere, right? So it could be anywhere. Like if you multiply by some number here, you're going to get in the same line. It's going to stay in the same line. That's what it means, right? So I'll stop here.